We are the 2020 robotics team from the University of Technology's Clausthal. In this video, we want to give a short overview about our BHA design, our steering algorithms, and our drilling rig. In order to achieve this year's challenge, we optimized our BHA design to meet the requirements of the directional drilling task. Our drilling rig remained mostly the same as last year, since it was by then already optimized for directional drilling. The University of Technology's Clausthal participates this year the fourth time in a robotics competition. We thankfully appreciate the constant support of our sponsor Wintershaldea and the ITE Clausthal. Mechanical properties of the rig. This year's drilling rig remains the same that the team used in the previous year due to its optimization on directional drilling and our focus on trajectory competition. The rig consists mainly of two parts: the basic structure with the mud handling system, the electrical installations and the rock sample receiver, and our disconnectable traverse on which the top drive and the power pack are installed. The rotary table can freely move along a spindle up and down in order to follow the drilling trajectory and maintain the needed jacking of the string. In contrast to last year's installation, we changed our concept of a downhole motor into a surface power pack, which is mounted on top of the rotary table. The power pack used in this year's installation is a C3140 spindle motor from Technomotor. With a maximum rotational speed of 24,000 RPM and a power capacity of 0.55 kW, this motor is fitted to propel the flex shaft and the connected bit to its needed speed and torque. In order to propel the flex shaft independently from the main rig, a rotary decoupling system will be installed. With the help of the decoupler, cables and liquids can be injected into the system without the necessity of another installation system. Mechanical properties of the BHA. The BHA used this year consists of a modular system where the different parts can be disconnected in case of a failure. Our first design approach featured a bendable bearing ring, which was actuated by a single hydraulic cylinder installed in the upper part of the buttonhole assembly. The drill bit was propelled by an electrical downhole motor that was installed on top of the steering unit. The lower part of the system featured a sensor unit and a drill bit bearing and remained in the following concepts nearly the same as in the initial design. The sensor model consists of two half-circular shaped parts and is capable of measuring the position and inclination of the buttonhole assembly. In addition, the downhole weight on bit is measured here. It is also possible to measure the bending moment in x and epsilon axis and later to determine the force factor of the bit from these values. With this arrangement, the actual weight on bit can be determined more precisely because of the friction of the drill pipe and the supporting moment of the BHA wings is omitted. In contrast to the first concept, our current design is driven by a surface-mounted power pack and lacks the radial bearing unit. Instead, the BHA steering process is carried out by three independently from another expendable wings, which are actuated through built-in hydraulic cylinders that are controlled by surface-mounted stepper motors. These stepper motors are installed on top of the rotary table and are connected through hydraulic cables with the BHA. To prevent over-torquing of the bit, a safety clutch is installed above the steering unit. In case of stuck of bit, the system can circulate itself free and fatal damages can be avoided. The clutch is designed in such a way that three boards under spring pretension engage in bores which are located radially in the clutch bell, and thus the torque is transmitted via the shear forces. If the transmitting torque increases in a forcible manner, the bolts slip out of the slightly maneuverable bore holes and the clutch allows the flex shaft to rotate freely. In order to achieve the best possible performance in later operation, an adjusting screw has been designed to adjust the preload of the spring. In this way, an optimal can be determined experimentally.
This diagram shows the mechatronic circuits and arrangement of the modules of the drilling rig. The main controller on which the trajectory and drilling algorithm is executed sends target values via the CAN interface to the actuators of the rig on which small control loops are implemented. These actuators and the main controller also receive sensor data via the CAN bus, which is continuously sent to the network. The sensor data of the inertial measurement unit, the gyroscope, and the magnetometer are processed with a MARG filter, which is shown here and automatically converted by the algorithm to coordinates in quaternion format, which are output at the rig coordinates. In addition, the filter algorithm compensates drift influences of the gyroscope and iron influences on the measurements of the magnetometer. The representation of the values in quaternions allows a fast execution and therefore a high data rate. Here you can see the trajectory control algorithm. Basically, the given target coordinates are converted into target trajectory, and then it is converted into a target angle. The signal path shown below contains two cascaded controllers. The first controller determines a correction angle from the deviation from the target to the actual position. The following controller sends a correction signal for the deviation from the target angle to the actual angle to the actuators in the controlled system.
At last, we want to give a short overview of our team structure. Our team lead this year is Felix Odebrecht. In order to enhance working performance, we subdivided our team in the three separate branches: construction and design, programming and algorithm optimization, and electrical engineering. Our construction branch consists of Dominik Brichle. Part of the programming and algorithm optimization branch are Felix Krugmann and Henry Fischer. Our team member for the electrical engineering branch is Marlon Schulz. In advance, our support team for supplementary tasks consists of Raphael Nunes-Albermann and Max Hallermann. This year's team advisors are Wolfgang Holstein and Dominik Orgel. Our special thanks to the organizers and judges of this year's competition, and thank you for watching our introduction video.